Have you ever looked up on a clear night and wondered if any of those tiny points of light have a planet circling them where you could actually breathe the air? It is not a crazy question anymore. Since 1995, astronomers have confirmed more than 5,800 planets orbiting other stars. That number sounded like science fiction 30 years ago. But here is the part almost nobody talks about. Finding a planet is one thing. Proving it actually has an atmosphere is a completely different and much harder problem. Why does an atmosphere even matter so much? Because without one, a planet cannot hold onto heat, cannot shield its surface from radiation, and almost certainly cannot keep liquid water sitting on its surface. No atmosphere generally means no chance at anything resembling life as we know it. It is the difference between a living world and a dead rock spinning in the dark. So which planets actually have one? For big, puffy gas giants sitting close to their star, astronomers cracked this problem back in 2002 when the first exoplanet atmosphere was ever detected. Those planets are basically perfect targets. They are enormous, often bigger than Jupiter, and their atmospheres are thick and puffed up by heat, easy to spot even from many light years away. Small, rocky, Earth-sized planets are a nightmare by comparison. They are tiny. They are dim. And they sit right next to a star that outshines them by a factor of millions. Picture trying to see a firefly sitting 1 inch from a lighthouse beam from miles away. That is roughly the challenge astronomers face every time they try to study a small rocky planet directly. So scientists found a workaround. Instead of sun-like stars, look at red dwarfs, small, cool, dim stars that make up the vast majority of all stars in our galaxy. A planet next to a dim red dwarf is not drowned out nearly as badly. The contrast is far more forgiving, and suddenly, small rocky worlds become detectable. But red dwarfs come with a nasty catch. Despite being small and dim in visible light, many of them are surprisingly violent, blasting out X-rays and ultraviolet radiation, especially early in their lives. That radiation can physically strip a thin atmosphere away into space over millions or billions of years, like a hairdryer aimed at a planet for eons at a time. So here is the real question scientists have been chasing for years. Around these small, feisty stars, do rocky planets ever get to keep their atmospheres, or does every single one end up stripped bare? Researchers even have a name for the invisible line where this battle gets decided. They call it the cosmic shoreline. Think of an actual shoreline on Earth. Some areas stay dry land no matter what. Some are permanently underwater. And some sit right at the edge, sometimes flooded, sometimes not. The cosmic shoreline works the same way, except instead of water, it is about radiation and gravity. Planets that get blasted with too much stellar energy for their size end up airless. Planets on the safe side of the line get to keep their air. For years, the results were discouraging. Astronomers pointed powerful telescopes, including the James Webb Space Telescope, at some of the most promising nearby rocky worlds, like the famous TRAPPIST-1 planets. Over and over, the results came back the same way. Airless, no detectable atmosphere, or at best, hints too faint to be sure of anything. It got to the point where some scientists started to wonder if the cosmic shoreline was almost a hard rule. Maybe small rocky planets around these stars just never keep their air, period. So what do you think? If you had to bet right now, would you guess that small rocky planets around dim, feisty stars almost always end up as bare rock? Or do you think some of them beat the odds? Here is how scientists actually catch an atmosphere in the act, because you obviously cannot just walk up and take a breath sample from 48 light years away. When a planet passes directly in front of its star, from our point of view, A tiny fraction of that starlight grazes through the rim of the planet's atmosphere on its way to us. That grazing starlight picks up a fingerprint. Specific gases absorb very specific colors of light, like a filter, so astronomers can split that starlight into a spectrum and look for missing colors. One especially useful fingerprint comes from helium. When a star's high-energy light hits helium atoms escaping a planet's atmosphere, it kicks them into a distinctive, excited state that shows up clearly in infrared light. This helium trick had already revealed puffed up, escaping atmospheres on several large gas planets. But nobody had used it to nail down a clear atmosphere on a small rocky world sitting inside a habitable zone. Until now, roughly 48 light-years from Earth, sits a small, cool red dwarf star called LHS 1140. If you tried to fly there on a commercial jet, it would take you more than 50 million years. Orbiting that star is a rocky planet called LHS 1140b. It is one of the closest, best-studied rocky planets sitting inside its star's habitable zone, the sweet spot where liquid water could plausibly exist. This particular planet had already been checked before, more than once, using telescopes like Hubble and James Webb. Every previous attempt came back the same discouraging way. No confirmed atmosphere. A team of astronomers, led by researchers at Harvard and the Carnegie Institution for Science, decided to try something different. They aimed one of the most sensitive infrared instruments ever built directly at this planet. The instrument is called WINERED, mounted on a 6.5-meter telescope at Las Campanas Observatory, high in the Atacama Desert of Chile, one of the driest, clearest places on the planet for observing the night sky. On the night of September 23, 2024, they watched LHS 1140b cross directly in front of its star, along with its smaller, hotter neighboring planet in the same system. And there it was. A clear dip in brightness at exactly the infrared wavelength where escaping helium should show up. Not a faint hint. A real, measurable signal. The signal did not just flicker on and off randomly either. It built up gradually before the transit even began, stayed steady during the crossing, and faded out slowly afterward. Exactly the smooth pattern you would expect from a real trail of escaping gas. The team spent months trying to break their own result. Could it be contamination from Earth's own atmosphere? Could it be random flickering from the star itself? They tested every alternative explanation they could think of. None of the alternatives held up. This looked like the real thing, a genuine atmosphere, caught in the act of slowly leaking away into space. So let's get concrete about exactly what the astronomers found, because the details make this story even more interesting than a simple yes or no answer. LHS 1140b has 5.6 times the mass of Earth and 1.73 times Earth's radius. It receives 42% of the sunlight Earth gets, giving it an estimated surface temperature around 226 Kelvin, about -47 degrees Celsius, if it had no atmosphere at all. The excess absorption the team measured came out to 1.24%, concentrated at that telltale helium wavelength of 10,833 angstroms. That is a small number, but a real, statistically solid one. Here comes the twist. When the same team pointed their instrument at LHS 1140b again a year later, in September 2025, the helium signature was completely gone. That does not mean the first detection was a fluke. It means the planet's atmosphere is not leaking away at a constant rate. Some years the escape is strong enough to detect. Other years, it apparently drops low enough to disappear from view entirely. The team estimates the planet was losing roughly 200 million grams of gas per second back in 2024. That sounds enormous, and it is real mass loss happening right now. But at that pace, it would still take billions of years to strip the whole atmosphere away. The chemistry of what is escaping is just as telling. The upper atmosphere appears to be rich in helium and unusually low in hydrogen, exactly what theory predicts after billions of years of the lighter hydrogen escaping first, leaving heavier helium behind. And remember that neighboring planet in the same system, the smaller, hotter one closer to the star. It showed absolutely no helium signal at all, consistent with having little to no atmosphere left, exactly where the cosmic shoreline model predicts it should sit. To be clear, this does not confirm LHS 1140b is habitable, or anything like Earth. Astronomers still do not know what else might be in that atmosphere, whether it holds water vapor, carbon dioxide, or something far more exotic. What it does confirm is narrower and still genuinely exciting. A small rocky planet sitting in a habitable zone around a small feisty star can hold onto an atmosphere long enough for us to catch it happening in real time. And the tools on the ground right here on Earth, not just billion-dollar space telescopes, are now sensitive enough to prove it. That is a genuinely new chapter in the search for worlds beyond our own.